So the next thing we're going to talk about is the squeeze theorem, and we're going to use this to find the derivative of sine. And if you remember, we weren't able to do it because I hadn't done this yet. Now, you might say, Mr. Adler, just tell us L'Hopital's rule. No. You're going to sit, you're going to watch this. If you don't want to watch, that's totally fine. But in university, you might have to sit in a lecture hall and take notes on this stuff. Squeeze theorem goes something like this. Squeeze theorem. The squeeze theorem is that if you have three functions such that f of x is less than or equal to g of x, which is less than or equal to h of x, okay, for x in an open interval, okay, containing C, but maybe not, maybe not C. So the idea is, the visual is, you have these three functions that are like above and below each other. So here's f, here's g, and here's h. No, I'm sorry. Here is f at the bottom, because it's the middle is g, and the h is on top. That's the idea. And this is we're looking at an open interval. So we're kind of like looking at like this region right in there. And they all contain C, but maybe they don't. Now, I'm going to change the picture a little bit to make it look kind of like this. I'm going to change the picture to kind of look like that. And here's F. I'm going to kind of change it like that. Now, once again, this is C. It may or may not be part of the function, but like that's the idea. They're all approaching it, but it's HGF, okay? Now, I'm also going to tell you that the limit as x approaches C of f of x is equal to the limit as x approaches C of h of x. You know this. That's the idea. You know that the little function approaches, you know that the little function as it approaches C is L, and you also know that the big function as it approaches C also approaches L. What does the squeeze theorem tell us? It tells us then the limit as x approaches C of g of x equals L also. Let's see an example of this. What is that? Let's see an example of this. So what is the limit as x approaches 0 of x squared cosine of 9 over x? So you're looking at it and you're like, Mr. Adler, how are we going to figure that out? We don't know that. We don't know limits about that. Well, you do know a couple of things. Tell me about cosine. Tell me about cosine. Well, you do know that cosine of anything is bounded. We know that cosine of 9 over x is bounded between -1 and +1. Right? You do know that. You also know that because x squared is greater than 1, I could multiply everything by x squared. What equals. I could multiply everything by x squared and not x squared, and not worry about flipping the inequalities. And so what I'm going to do now is, this is kind of cool, I'm going to take the limit as x approaches 0 of -x squared, which is less than the limit as x approaches 0 of x squared cosine 9 over x. Can you see me over there? See me. Sorry. I'm going to take the limit as x goes to 0 of -x squared, which is less than the limit as x goes to 0 of x squared cosine 9 of x, which is less than or equal to the limit as x goes to 0 of x squared. Well, the trick is just see what you can substitute. And you say, well, you know what? This is 0, and that's 0. Therefore, by the squeeze theorem, that's 0. That's the squeeze theorem. Now, why do we need it? Why do I need to waste your time on this? Mr. Adler, tell us about L'Hopital's rule. Not yet. So the question is, what is the derivative of sine x? So this is, you're going to see, if you see this, I'm just showing you. You can skip through this if you don't want to see this. This is fine. Once I recall the limit as h approaches 0 of sine of x plus h minus sine of x over h. If you recall, this was first principles. Remember, we kind of had like, if you remember, it was like the slope. Yeah, if you recall, it was like the slope. Remember, 2 points were here, and we drew the line, and this was like x, and this was x plus h, and we kept shrinking it together, so we had the tangent line. We were looking for the tangent line. And that's where the limit came in. Now we have a language of limits, so we can go through this. So we know that x plus h, this is long, skip through this if you want, put it on fast. It's the sine of x cosine of h plus sine of h cosine of x minus sine of x over h. Okay? Let's continue. Let's continue. What I'm going to do is I'm going to split these up into the limit as h approaches 0 of cosine of x sine of h over h plus the limit as h approaches 0 of the sine of x cosine of h plus 1 over h. So let's take a look at this first one. So the question is, how do we find the cosine? So we have two things. We're going to have to find the limit of sine of h over h, and we're going to find the limit as h approaches 0 of cosine of h plus 1 over h. First of all, I can pull the cosine of cosine of x outside because I'm dealing in the world of h right now. So this comes out. So the cosine of x, the limit as h goes to 0 of sine of h over h. How am I going to do with this? I'm going to use the squeeze theorem. The idea is we're going to compare areas of circles. So I'm going to take a big circle, right? And I'm going to draw a line in here. So here's my first triangle. Now, if this is 1 and this is in radians, that's theta, what is the area of that triangle? So you say, okay, Mr. Adler, well, this is cosine and this is sine. Therefore, the area of this triangle is 1/2 sine times cosine. Now, the next thing is I need to squeeze. So what's a little larger than that triangle? Well, it turns out this sector is actually a little bit larger than that triangle. So what's the area of that sector? Well, here's the cool thing. If this is theta, and we know the circle is 1, that means that this length, arc length, is also theta. Because we're in radians. That's a great thing about radians. And we learned that the area of a sector is 1/2 the radius times the arc length. Well, so it's 1/2 1 times theta. Now I need something a little bit larger to squeeze all this in. So I'm going to use a really big triangle here. I'm going to expand this out. This length is 1. This actually is tangents. And if you remember from 9th grade similar triangles, sine over cosine is equal to something over 1. Well, that's tangent. So this actually is less than, the area of this big triangle is 1/2 base times height, or 1/2 sine over cosine. Okay? The next thing we're going to do is we need to manipulate that fraction. So you might say, okay, well, so these are thetas. I guess I should use h. I guess we can use theta. So the idea is, Yeah, so the idea is, what is the limit as theta goes to 0? Same idea, theta h. So what's going on here? Well, I have to do a little manipulations. So what I'm going to do is I'm going to divide everything by sine. Let's divide everything by sine. Yeah, let's multiply everything by 2. 2 over sine. Now, because we know that sine, we're going to keep sine positive because it's right in the positive. We're not going to worry about flipping the inequalities. So we have, what do we have here? We have cosine is less than or equal to theta over sine, which is less than or equal to, what do we have? 1 over cosine, right? Now, next, what happens? Let's think about this for a second, because I don't want theta over sine. I want sine over theta. How are we doing for time? We're good. I don't want theta over sine. Remember, I want sine over theta. So let's flip everything. So 1 over c, sine theta over theta, and cosine. Well, what happens when I take the reciprocals? I actually, flip the inequalities. And so we have this new inequality. And so the question is, so the question now is, what's going on? Well, if I take the limit as theta goes to 0, well, cosine of 0 is 1. So let's think about this. So 1 over cosine of 0 equals 1, and the cosine of 0 equals 1. Well, therefore, sorry. So let's take a look. So I'm going to substitute the 0 in here. So 1 over cosine of 0 is 1, and the cosine of 0 is 1. Therefore, the sine of theta over theta equals the limit as theta approaches 0 equals 1. Next, what's that cosine? Let's work on that cosine a little bit. The trick is, let's work on this. So we have sine of x, the limit as h goes to 0, of cosine of h plus 1 over h. The trick is, here's the trick. And once again, you can say, Mr. Adler, just use L'Hopital's rule for all of these. No, let's go through this. The trick is cosine of h minus 1. It's almost like rationalizing. And so you're going to do cosine of h minus 1. You're going to end up with cosine squared minus 1 over h times cosine of h minus 1. Okay? This is going to be negative sine of h over h cosine of h minus 1. I know. Sorry, I'm turning the air conditioner on. So let's continue. What are we going to do here? Well, the trick is we're going to introduce an h over h. I'm going to bring in an h and an h. Oh, sorry, this was sine squared. So what we have here is we have an h, we have a negative, we have a sine over h squared, and we have 1 over cosine of h. Actually, this is minus 1, I'm sorry. This is minus 1. This is minus 1. This is plus 1. what we have is, and then when we take the limit as h approaches 0, we have this is 0, this is 1 squared, and this is 1/2. Final answer, 0. Therefore, to conclude, therefore, once again, therefore, look at that over there. Here, therefore, the limit as h approaches 0 is equal to, what do we have? We have cosine x times 1 plus 0, or cosine x. And therefore, the derivative, if f of x equals sine of x, the derivative of x equals cosine of x. Once again, Mr. Ryler, why can't you just tell us Welby's house rule? Well, yeah, I could, but I'm not. Let's go on. We have 2 more pages. Continuity. Let's continue. You know what? I'm stopping this video.